This is One Universe at a Time. I'm Brian Koberlein. Farmers know that the grain piled up in a silo might look solid, but if you stand on it, you can get in trouble real quick. Granular materials like wheat, sand, or snow behave in different ways than solids or liquids. Today we're going to talk with Dr. Scott Franklin, a professor of physics at Rochester Institute of Technology, about this common but interesting kind of material. One of your areas is granular materials, right?
Yep.
So to me that comes to mind the idea of things like sand.
Yeah, exactly. It's surprising how much starts with regular sand that you take from the beach. Matter of fact, I got a project now that was brought to me by someone who's studying coastal sand.
Okay.
And it's all about how sand, when it mixes with different types of sand, like really small silt,
Right.
becomes really soft. So he's got this picture of a truck that's driving on the beach, and then it suddenly hits this region of the beach where silt has come off the mountain,
Right.
and it just like sinks and stops.
And it sinks
And
into
now they're
it.
trying to get the truck out.
From a physics standpoint, it seems to me that all of these materials are classical in nature. They just depend upon Newton's laws.
Yep.
What makes this a separate area in the sense that it seems like, well, it's just particles interacting? How is that any different than rocks or planets?
A couple of things. I mean, first is the fact that you've got 100,000 or 10 million of them.
Okay.
So that when you want to actually figure out what's going on, it's not very productive to pay attention to each individual one.
Mm-hmm.
So when you do fluid mechanics, for example, you could have a model for each water molecule. But if you
Right.
want to know how a cup of water works, you don't do that. You try and
Right,
think
use
of it
the
as a
fluid
whole.
equations.
So the holy grail of granular materials is to come up with a set of equations like the fluid equations,
Okay.
so that we don't have to know where everything is. But the other part, which is not true in fluids, but is true in sand, is that friction is really complicated.
Okay.
And if you want to know something about regular friction, it's actually kind of hard because it can respond to forces. And so if you just know where every particle is, you don't necessarily know what the frictional forces are, which means that the forces in this material are unknown. They tend to not be uniform and smooth like you'd get in a fluid.
Right.
And the fact that they're not uniform and smooth, which is because of these frictional contacts, has some really important consequences. Like it's what blows silos apart.
Okay.
And silos
Yep.
blow out the side. They don't actually
Right.
collapse underneath.
Right.
And they do that because granular materials in sand tend to create these force chains, which can be a lot larger than the actual total force that's being pushed down from the top. Kind of like how if you imagine trying to hold a wire and you want to hold it absolutely horizontally.
Right.
And you're only pulling horizontally and you're fighting gravity, you have to pull really, really hard
really,
to
really
keep
hard.
it taut. So the same thing gets set up within sand piles. You have these grains that form bridges that are trying to balance gravity, but they're
Right.
doing it from
But
an
they're doing
from
it
an angle.
almost horizontally, and so you get
Exactly.
these massive forces
Massive force
horizontally.
chains. And that's
Okay.
why grain silos blow out from the side.
Right, right.
And the forces can be 6, 7, 10 times larger than the total weight
Right.
of what's in there.
Well, you'd hear about this sometimes.
Exactly.
You know, I mean, growing up on a farm was exactly that, and it's
Right.
like, yeah, you'd see these things, and it's like, wow, that doesn't seem like it's just
shouldn't-
go with grain. Why? How can it explode?
Right.
You
So-
know, people would say like water or something or heat, and it
doesn't do that.
It doesn't do that. Okay.
Yeah. And then the other topic in jamming, and it also is brought about not necessarily only because of friction, but is the jamming. Right? I mean, water
Right.
will flow through a hole
Right.
until it's empty. But, you know, if you grew up on a farm, you have a grain silo, you know it jams.
Yeah, and that don't step on top of it. You can create cavities.
That's
and
right.
It can collapse and trap you and stuff
And
like that.
we're not really good about figuring out ways to move these materials. So
Right.
so it still is the case that when things jam, you basically poke it with a stick and get out of the way.
So is that specifically a thing of granular materials? Because I think of something like ketchup.
Right.
That everybody talks about. And to me, that seems like a fluid. It may be a very viscous fluid.
So ketchup's a non-Newtonian fluid.
Okay.
In that it's not like regular water.
So that's like the cornstarch and water
Cornstarch,
experiment.
exactly,
That
yeah.
it seems somewhat solid until you hold it.
Exactly.
And then it kind of goes as a blob.
So its behavior depends on how fast you're trying to make it do something.
Right.
Jamming actually happens in a lot of different systems. Glasses are one of them.
Okay.
Right. So if you look at your window glass, contrary to popular perception, it's not a liquid that's flowing.
Right.
It's in a glassy state. It can go from liquid to solid a few tenths of a degrees.
Right.
I mean, we're talking enormous changes in the structure or in the behavior based on only a little change in temperature.
Right.
And actually, there's not much change in the structure. So if you were to take a picture of your window glass and you were to compare it with liquid glass, you wouldn't be able to look at one and say, oh, that's liquid because look at all the space the molecules have. It really is not very different. Somehow that fraction of a change in
so
density.
It's not solidifying.
It's not
just
solidifying.
jamming?
It's jamming.
So glass is just like a jammed material?
Exactly. Glass is a jammed material, and it's unable to get out of that.
That's so wild, because we think of it as it's just
solid.
It's something that's solid. I guess I would always have imagined it as more of a non-Newtonian fluid in the sense that given enough time on a large scale, it would gradually sag. But no, it's
that
a
with
jammed
glasses,
material.
that time scale diverges. So it's longer than anything is possible willing to wait.
So the idea that it's lower, when you see the old panes and you say they're thicker on the bottom, that's just bad manufacturing?
There's a reason for why it's thicker on the bottom. I think it actually is structural. They made it that way to withstand the weight. But it's not because it's not because it's sagged. Right. So we study jamming in a lot of different systems. I mean, there are simulations of regular window glass, but you can't directly look at that. People use colloids, which are small particles, width of a human hair size or smaller.
Are they in a fluid as
well?
They're
in a fluid and they're bouncing around.
Colloidal suspension or whatever.
Yep, a colloidal suspension. And you basically increase that the number of particles in there, and at some point it jams into a glass. And it does that when there's still plenty of room to put it in if you packed it nicely in a crystal. Okay,
so there's still space between, but
there's still
just the
space
arrangement
between.
of it.
It's just the arrangement.
It's just, it can't move.
Exactly.
So it's a traffic jam.
It's a traffic
jam.
that
there's the guy ahead of you still has half a space in front of you.
You've got space, but you can't get there. So that's studied at the small scale, and the same thing is happening at the granular scale. So when you look at how...
Granular is like sand size or
sand
larger?
Size, yeah. So sugar size, sand size, not quite flour. Flour's still small enough that it sticks together. It's a powder.
Okay. So if there's some type of cohesion, then it's more like flour, or is
no,
it
you can talk about wet and cohesive granular materials.
Okay.
Things that stick together. So like when you build a sandcastle, you put water in because it makes the sand stick together.
Right. Or flour will tend to get like electrostatic charge.
So flour is small enough that those electrostatic forces can hold them together.
Right.
Granular materials are more
really
on the sugar, sand.
Okay.
But they also show jamming. So there's a whole field of study that's all about how do things jam and do we see similar behavior in these systems, whether they're liquid glass, colloids, sand. Actually, the conference I was at this summer, there was a talk on flow through exits and how if you put something that doesn't move in the exit, maybe a little ahead of the exit, to force the things to go around it, then it breaks up the jams.
It breaks up the jams,
And the example they used was actually sheep exiting a barn. And so they put a big thing about, 3 feet before the door.
Right.
So that as the sheep were running out the door, they couldn't all get to the door. They had to go around this thing. And they showed that more sheep got out.
That reorganization. It's weird thinking of sheep as granular materials.
Absolutely. Same thing happens with people. It's why when they build exit doors, they have like door frames in the middle.
And they're in the middle because they force you to go to one side, and that way you don't jam.
Exactly.
It's kind of disturbing that, let's assume people are just chunks of sand, and it works.
Within reason.
Within reason, yeah. I mean, some of us are always a little special. But
Right. Ants follow a classic equation for transport.
Okay.
And so the question is, how come people don't? And the answer is, one, people care about collisions.
Right.
And ants don't. They'll just run into them.
Yep, they can run into each other.
And people rubberneck. And ants don't.
so we look at, there's that poor guy, and then we're slowed down all of a sudden.
So if we behave more like ants, we would not have traffic jams.
So we're dumber than ants.
We are dumber than ants in many ways.
When it comes to moving out of a stadium.
Exactly.
That's funny. I guess one of the things I see with when you talk about like jamming and critical transitions is things like avalanches. People are, at least in movies, were familiar with that one snap, that shift, and then everything goes at once. So that would kind of be the opposite of jamming. In some ways, it's that interface, right? Like if you are jammed, what unjams you? Gets back to the point I made earlier about not being able to tell that window glass is any different from a liquid because structurally it looks the same. If you just take a static image of it, you don't know if it's capable of moving or not. You don't, and you also don't know where the weak points are. Right. And so one of the issues that we're doing here at RIT is starting to look at things as they move and ask, is there anything about the picture of where everything is that tells us where things are likely to move? So just based on the position of things? Just based on the position. It would seem to be like a very easy answer. It's where the gaps are. You would think. But it turns out not to be the case because, a lot of times when you have that big gap,
one thing moves into that gap, but then nothing else happens. Right. So it has
everything settles and kind of blocks it off.
Exactly.
Okay.
I mean, it goes back to this idea of these force chains that are in there.
Right.
And these force chains are really, really long.
Right.
So what's important is not that a particle moves, but a particle that is part of this much, much longer thing is the one that moves.
I know we do that with emptying grain silos. The cavities were always a challenge because it would look solid, and you could even test it. You'd whack on it with a stick.
It would feel,
and it would be perfectly solid, and you figure, well, I can step out on that, and you do not want to do that. You really don't want to do that.
I think I read something like 20 to 40 people die every year because they're caught in silo accidents for exactly that reason. So one of my research projects is on really long, thin sticks, which behave in different ways.
Okay.
Because you can get really, really strong, like toothpicks, like spaghetti, like straw, because things like that can form really, really strong piles that are really low density because they're mostly air. And one of the pictures I have is a log jam on a river because they used to float logs down, right? And when it jammed, they would pay someone to walk
out on there,
walk out on the log,
with a stick.
and then and then as soon as everything started moving, he had to figure out some way to run on the moving. I mean, it was an awful, I can't imagine that job.
Yeah, get the young guy on the kid.
Right,
here, go out there. You can do that.
The idiot who doesn't realize that it's easy to get out there, but it may not be so easy to get off.
Yeah, reminds me of like a lot of the stuff. I mean, my more familiarity are things like with grains and stuff, and you would do a lot of things with shaking.
Yes.
So you would have the entrance, but you would have some vibrator that would shake it, and the idea is that will just kind of keep it in flow, keep it from jamming.
Yeah, it breaks those frictional contacts. The idea is that if you shake it for a split second of time, those grains
they move
fluidize, they move apart.
Right,
now you don't have the friction. Yeah.
Okay.
So there's some really interesting research on what happens as you shake and how that looks more frictionless.
Right.
But it's possible to jam even
you
with frictionless.
You can shake it into a jam.
You can shake it into a jam, right? I mean, the idea that you have these force chains doesn't depend on friction. Friction certainly helps it, but it doesn't depend on friction.
Well, that's weird because I would think that friction would be it. So you're saying that you would have force chains even if you had perfectly frictionless spheres.
Because if they weren't placed in a crystal, right? If you start them at random, then they're off axis. And so they're not evenly resting on what's below. So they don't smoothly divide their forces. And at any time you don't smoothly divide, you end up with the possibility of aggregation and force chains.
So friction plays a big role, but friction isn't necessary. You could model, for example, perfectly frictionless spheres.
Absolutely.
And they would still jam. Wow, that's just fascinating because you would think in basic physics, frictionless things, although they don't really exist, we think frictionless things would just slide.
Right.
That they'll always slide. So any slight difference would cause it to slide completely off.
Yeah, and it really is they're frustrated by the geometry, by the fact that they're crowding in with all their other neighbors.
So the shape is almost more critical.
Well,
I mean, they're both playing a role.
They can still be perfectly symmetric. They can be spheres and disks and stuff, right? It's the fact that they're frustrated, that you've got so many of them that it's almost impossible that by chance you would get the perfect crystal formation. I mean, in regular solids, you've got all of this thermal energy. So atoms are moving around all over the place.
Right.
And so they have time and a way to find their sort of...
To find that space.
To find that crystal packing. One of the reasons that the size of granular materials is so important is that thermal energy isn't there. I mean, yes, the particles are shaking around because they're hot, but they're shaking around at a completely negligible rate.
Right.
So it just doesn't matter. So it really is their size, right? So which is why shaking kind of helps you, because if you shake, then you're putting energy in.
Right.
You're acting like temperature.
Right. It's kind of, it really is. It reminds me a lot like a traffic jam, that idea that even though it's frictionless, we're not sliding against each other, but we do jam up, and then it takes some type of thing to get us going again. Yeah.
So we once actually thought of an experiment where we would shake staples, so put energy in that way, and compare them with ants. Because ants are essentially granular materials,
right?
But they're alive,
right?
And if you freeze,
so if you shake ants,
if you freeze ants, they slow down. So and you can unfreeze them, and they come back to life. So there's this whole idea of a matched experiment of like shaking staples and ants at different temperatures.
And there's a correlation there?
We never actually explored it. We're still working on it. But
these poor ants. Freezing ants for science.
They're fire ants. I have absolutely no sympathy for them.
Okay. Well, there you go then. You're listening to One Universe at a Time. I'm your host, Brian Koberlein. We've been talking with Dr. Scott Franklin, professor of physics at the Rochester Institute of Technology, about granular materials. In the second half of our show, he'll ask the questions and I'll answer. Today, Dr. Franklin is curious about the 4 fundamental forces of nature.
So, Brian, you do work on the 4 fundamental forces, they're called.
Yeah, actually, astrophysics, but yeah, the 4 forces come into play.
And I know 2 of them, gravity and electricity. That's what people most familiar with. Talk about the other ones. Like, how do we even know that they're there?
As they typically list them, the 4 fundamental forces are gravity, electromagnetism, and then 2 nuclear forces. One is called the strong nuclear force. The other one is called the weak nuclear force. In basic terms, I think there was a XKCD comic on it that said, you've got electromagnetism and gravity. The strong force holds nuclei together, and the weak force, something radioactivity, which is how they're normally described, because the weak force is what kind of drives radiometric decay, and the strong force is what holds nuclei together. And so on a broad level, that's what they are.
So how do we know that there is such a thing as the weak force?
We know there's something on the weak force because we can see the interactions. I mean, we connect it to radioactivity because radioactivity was the first thing that we saw. Mm-hmm. What you would see is, Marie Curie, for example, looking at radioactive decay, she found out 2 things, among other people who were working on it. One was the particles or the stuff, the rays that are coming off of this radioactive material has much more energy than it should. You're getting more energy released than you would think based upon the temperature of the atoms or anything like that. And the other thing was you would change the element. So the isotope would change. So you would have one material decay into a completely different element. And that meant that something must be going on in terms of the interior of the elements. So we know now, for example, that the elements are determined by how many protons are on a nucleus. And if you're changing isotopes, if you're changing from one element to another, somehow that proton or some protons are changing into neutrons. So you're getting a decay of neutrons or protons within the nucleus of an atom.
So one way to think about forces at this level is really connected to energy.
Right.
As well.
We call them forces because that's what people are familiar with, but they really should be interactions.
Uh-huh.
So there's a weak interaction in the sense that it's mediated by the weak field. And that's what causes the shift from neutrons to protons, protons to neutrons.
And is that kind of the same thinking that led to the finding of the strong force, or is it a different type of interaction?
Well, yeah, the strong force is a different interaction. The early ones were actually the Yukawa potential. So Yukawa looked at the forces between protons and neutrons, what we call nucleons. Mm-hmm. That seemed to look somewhat like a force. What it didn't explain is why we were constantly getting more and more particles. The idea is that we have, early on it would be protons, neutrons, and electrons. And you can do the Rutherford experiment, for example, that shows that the nucleus of protons and neutrons is really dense, and then there's this cloud of electrons around it. What holds the nucleus together? And one of the early ideas was that somehow neutrons were kind of acting as a kind of glue. Right. And that's where the Yukawa force or the Yukawa potential came in, that there was some kind of force between neutrons and protons.
That was larger than the electric repulsion.
That was larger than the repulsion of the individual protons because of their charge. Right. So as we started doing particle physics, we started finding particles that weren't protons and neutrons, and they weren't electrons. So we would find neutrinos, we found positrons, we'd find all of these kind of strange particles, some of which looked like protons or neutrons. They were baryons. Mm-hmm. And some of them that were similar but lighter in general, and so we called them mesons. Mm-hmm. So the pi meson, for example, was thought to be an interaction between protons and neutrons.
And when you say see, we're mostly looking at like cloud tracks through fields and recognizing that they don't move as much as the protons. So
right. There's a good way to look at particles where you can say, now we use like a bubble chamber or a scintillator, but in a magnetic field, in an electric field, you can see the path that charged particles take because they disturb either a cloud and cause little droplets to form along a path, or they create little bubbles in a supercooled fluid, and then that way you can see those paths, and you can calculate what their mass is, what their charge is, and things like that. So we were seeing all of these things that we could identify as different particles, but they were far more. We got this particle zoo that didn't seem to fit anything. What came was the quark model. When you start looking at, well, maybe these particles are all made out of even more fundamental particles that we call quarks. And that fit, but that meant that the interactions had to be between quarks and not just between protons and neutrons.
So is the strong force then a force between quarks?
Yes.
Okay.
So the strong force is an interaction between quarks in a similar way that the electromagnetic force is between charges. So if you look at the force between charges, we think of them as kind of a classical force, but on the quantum level, they're actually interactions of quanta in the field. And so you have photons that can interact with the charges. In the strong force, you would have a strong field, and what are called gluons are the quanta of the strong force, and they interact between quarks.
And you have similar things for the weak and gravitational?
Yeah, there's something called the gravitational is an interesting one. For the weak, there are W particles and Z particles. They interact on the weak side. The gravity, if you do the basic calculation, you get something called a graviton. But the problem with gravity, and why gravity is the one that we really don't understand, is that it doesn't follow the same rules, in the sense that we can look at the other three forces as an exchange of quanta and calculate the forces that way. But gravity in general relativity is a curvature of space and time. It's an inherent property of space and time. It isn't a field in space and time. So the other forces will assume a kind of background of space and time that isn't affected by the interactions. Whereas with gravity, when you try and bring general relativity in it, the interactions are an interaction of space and time itself. So you can do approximations. You can say, well, any deviation from flat is like a field in a flat background, and you can quantize that. And that would be a kind of semi-classical approach to gravity. And that you get out the graviton. Trying to do the whole of space and time is problematic. The math doesn't like the math of general relativity. So this is why you get into string theory or loop quantum gravity or other much more complex approaches
to try and quantize this curving surface.
Right. So you kind of get, the strong, the weak, the electromagnetic, they fall into the standard model. And then there's mod over here. That's, the other thing that's just not really fitting into everything else.
Which is the one we noticed first and thought was the easiest.
Right. And on a basic level it is. But then when you delve into quantum, as soon as you get into quantum mechanics, it's the hardest.
Is one of those reasons that gravity is at the macro scale, like we notice it, and we wouldn't notice the strong and electro-weak unless we were able to look at individual particles. And
the big thing with gravity is it has two properties. Like electromagnetism, it can work on really large distances. And so we can see those effects. The other thing is that gravity can't be shielded. In electromagnetics, you can have positive and negative charges in an atom, for example, and they can become neutral. They can balance out. And so you wouldn't notice them. You don't really, even though it's a stronger force than gravity, you don't notice it that much. But gravity, you can't. There's no positive and negative mass, and so you can't cancel it out and make it zero. So mass will always be a force there.
Is that true for the strong and weak forces as well, that you can shield them out, or are they completely different structures?
No, you can shield them out. The strong force is actually interesting because instead of positive and negative, there's three and then three antis. That's part of the reason why they call it the color forces. If you look at the mathematics, it's not that they actually have color.
Right.
But what you can do is you can say, okay, well, if you look at red, green, and blue, green, and blue, when they combine, will make white, which is color neutral. And so the math works exactly the same for gluons. And so you would say, oh, well, we'll call it a color charge red, green, or blue, or anti-red, anti-green, or anti-blue.
Mostly because when you put the three of them together, you get neutral.
You get neutral, right. And so visualizing in your head, you say, well, that follows the same mathematical rules, so...
Do you get the same rules for like addition where red and blue works some way? And
yeah, you do. You can actually look at the colors combined and then you can cancel them. Typically what happens is you get like protons and neutrons, what we call baryons, would be a red, green, and blue.
Okay.
And then...
So color neutral.
Right, they're color neutral. And mesons, so pi mesons and things like that, are a color and an anti-color.
So you want neutrality for stability.
You want neutrality, right. And in fact, it forces neutrality because the gluons themselves, unlike photons don't have charge. So they don't care about each other. They only care about the charges. Gluons carry charge, so they carry color. And so they interact with themselves.
They want to attract things to make themselves neutral.
Right. So if you try and bring two colored particles apart, the gluons tend to go right along the line. It's called a flux tube. And if you do that, it gets more and more energetic until it snaps, and then it just forms new particles, and then they become color neutral.
Too.
But they're not into specific colors. So like you can say with a proton, it's red, green, and blue, but it constantly flips. It's constantly changing because the gluons are exchanging colors back and forth.
So electricity is stronger than gravity in some cases. Many cases. We probably just didn't notice it because there are all these positive and negative charges that made it neutral.
Right.
Does that also work down the chain where weak force is stronger than electromagnetism at the right scale and strong force is stronger than weak at the right scale?
Yes.
What are those scales?
Usually you take the strong force as 1.
Okay.
And then I want to say it's something like 1 over 137 for the weak, and then it's 10 to the minus 6th.
So the weak force is 37 times weaker than the strong.
Yeah, I think 137 or
137
something like that.
times. Fine structure constant.
Yeah,
yes.
I think that's where it is. And then there's a hierarchy of one being stronger than the other.
And and electricity and magnetism or electromagnetism is 1,000,000 times.
Something like that. And then gravity's even tinier than that. So gravity's almost negligible in terms of the strength of its coupling.
When you're at the distance where the strong force is 1.
Right.
There must be a crossover, though, right? I mean, if you're far enough away, the strong force falls off really fast, and eventually we notice gravity, not strong force.
Right. What happens is, for the color forces of the gluons, because they interact with each other, instead of getting the traditional inverse square decay that you would for electromagnetism or gravity, you get an exponential decay.
Oh.
And so what happens
much
is,
faster.
it really, really close, it's actually repulsive. So that's why nucleons don't collapse into a singularity.
Must be, right?
But if you get far enough away, you get this exponential decay. So there is a critical point. It's around, the radius of a nuclei, coincidentally. And so you get these clusters. Part of it is because, the exponential decay means why the nucleus of the atom still kind of retains its identity of protons and neutrons. It doesn't just become a single ball of quarks.
Because it's spread out over that length scale that's larger than a proton or a neutron.
Right. So what happens is if you have quarks in the nucleus, they kind of still clump into protons and neutrons that exchange forces between each other to hold the nucleus together. But the nucleus is not just a uniform ball of quarks.
And are there experiments that show the non-uniformity of the nucleus?
You can look at decay rates and stuff and model them based upon the stability of the neutrons. That's part of the reason why you can have stable and unstable atoms that are different isotopes. Because between protons and neutrons, the weak force is generally that Yukawa force. It's generally that interaction. And so you can get stability and instability, even different from, just the decay of a neutron, for example.
So if gravity and electromagnetism are 1 over r squared and strong is exponential, what's weak?
Weak is also exponential.
Okay,
but it's exponential because the exchange particles have mass.
So are there length scales that you pull out of the strong and weak force because of the exponential decay?
You can.
And if the strong force would be probably exponential on a diameter of a nucleus.
Nucleus, yep.
And then the weak force is the diameter of a proton or neutron, or
it's on a similar level.
Okay.
So it's why if you have two nuclei that are in atoms in a molecule, for example, you don't get one triggering the other by a straight weak interaction, but you get within nuclei next to each other, they can radio decay.
And any way to use these energies to generate power? I mean, is that what nuclear power is essentially doing?
That's what nuclear power is. Nuclear power right now, when we talk about nuclear power, it's fission decay, so it's just radiometric decay that way.
And that's weak force?
That's weak force.
Okay.
Yep.
But if we could figure out a way to tap the strong force...
It would also be the weak force indirectly because you would be smacking protons to create helium.
Okay.
And the only way to do that is to smack two protons together. You have to make deuterium. You have to start with deuterium. And that actually comes from a weak interaction because two protons come together and then one decays into a neutron and then you're okay again.
Got to make sure you're safe.
That's right. But yeah, fundamentally, we're all nuclear powered.
I like that idea that fundamentally we're all nuclear powered.
Yep.
Must be funding in there somewhere.
There's gotta be. We've been talking with Dr. Scott Franklin, a professor of physics at the Rochester Institute of Technology. Our program is produced at RIT with support from the RIT College of Science. I'm your host, Brian Koberlein. Thanks for listening to One Universe at a Time.